In this video, we're looking at a vertical Atwood machine with a heavy disc pulley, and this is framed in a very general way. We have one hanging mass of m, one hanging mass of 2m, and then the pulley itself has a mass of m and a radius of r. What we're trying to find is the speed of the system after it's fallen through a distance of d. So the heavier mass 2m is going to fall downward, the little m is going to be pulled upward by a distance of d. So we want the final speeds of those masses after they've evolved through a distance of d. And the new complication in this problem is that some of that kinetic energy goes into the rotation of the heavy disc pulley as well. So it's going to end this process at an angular speed of omega, while the hanging masses will end the process at a speed of v. So we apply energy conservation and say E initial is equal to E final. And we have to define the vertical coordinate carefully for each of these hanging masses. What I'm going to do for the mass 2m is call its initial vertical position d and its final vertical position 0. And for the mass m, I'll call its initial position 0 and its final position d. So looking at all the sources of energy in the initial state, there's no kinetic energy because everything was released from rest. All I have is potential energies. And with an initial y-coordinate of 0, the hanging mass m has an initial potential energy of 0. So the only energy source here is just the potential energy of my larger mass 2m. That's given by the mass times gd. So I end up with a 2m gd for my initial energy. In my final state, if I just account for the potential energies first, because my larger mass ends up at a coordinate of 0, it has no gravitational potential energy, but the mass m has a potential energy of mgd. All right, so we can see why we end up with some kinetic energy in the final state because our total gravitational potential energy has decreased. So in our final state, we also have 3 sources of kinetic energy. That's the translational motion of each mass plus the rotational motion of the disk. So we'll just handle the biggest mass first, 1/2 times the mass times its final speed squared. The smaller mass, 1/2 times m times v squared. And finally the disk, and that's 1/2 I omega squared, where I is the moment of inertia, and for a disk, that's 1/2 mr squared. And there's our omega squared, the final angular speed squared. Now in our final state, each mass is moving with a speed of v. That's the same as the speed of the string, and because the string is not slipping, that means it's the same as the speed at the outer edge of the disk. But we know that speed at the outer edge of the disk is related to the angular speed through the relationship v equals r omega. And I'll post a link to the video where I first discussed that relationship between the tangential speed and the rotational speed of an object. So v is equal to r omega, and conveniently we see an r squared omega squared sitting in our expression for the kinetic energy of the disk. Well, that's just v squared, where v is the translational speed along the edge of the disk, which is the same as the translational speed of our hanging masses. So now every one of our kinetic energy terms has an mv squared in it and some constants out in front, and we need to get these all combined. I'll go ahead and cancel an m from every term in our energy conservation equation before I write down the next step. And I may as well subtract a gd from both sides while I'm at it. I had a 2gd on the left and 1 on the right, so I'm left with 1 on the left. So I have gd is equal to, let's see what our first term is. 1/2 of 2 gives me a 1v squared, and I'm going to factor the v squared out. My second term has a 1/2 v squared, and my third term is a 1/4 v squared. So we'll combine our fractions with a common denominator of 4. 1/4 plus 2/4, that's the same as a half. So that gives me 3/4, and then plus the number 1, which is 4/4. So I end up with 7/4 v squared. And now we're just about to solve for v. We have to multiply both sides by 4/7 and square root the result. So I end up with a 4gd over 7 square rooted. Now in part B, we're asked to compute the percentage of the kinetic energy that ends up in each of the moving pieces of the system. So that's each hanging mass in addition to the rotating disk. And before we start, I'd like to just have a convenient expression for the total kinetic energy in the system. If we go back to our original energy equation, those 3 terms on the right give you the total kinetic energy. That was the kinetic energy of each mass plus the rotational kinetic energy of the disk. So I'll just call that KT for total. And if I just subtract that mgd term from both sides, I end up with an mgd on the left-hand side, which means my total kinetic energy is just given by mgd. That was the total change in gravitational potential energy. Now I can just go through each term in my kinetic energy expression and plug in the v that I found, and we'll figure out what percentage of the kinetic energy is in each piece. So we start with the 2m piece, K2m. That's 1/2 times 2m times v squared. The 1/2 and the 2 cancel, and I get an m times v squared. And now I plug in my final v. The squaring undoes the square root, and I get a 4gd over 7. So I end up with 4/7 mgd. In other words, 4/7 the total kinetic energy in the system for the final state. Now we were asked for a percentage here, so just getting a decimal approximation and multiplying by 100, we find that 57.1% of the final kinetic energy is in that larger mass 2m. Now we look at the kinetic energy in the smaller mass, and we can see that was a 1/2 mv squared, and we plug in our v, and we end up with a 1/2 m times 4gd over 7. One factor of 2 is going to cancel here, and I end up with a 2/7 mgd. And turning that into a percentage, I get 28.6%. Finally, we look at the kinetic energy in the rotating disk in its final state. I'll call that kd. And that was given by this final term in our original energy equation. And I could write that as 1/4 m times v squared. Remember, r squared omega squared can be replaced with v squared. V squared, again, is 4gd over 7. The 4's cancel, and I end up with 1/7 mgd. And this gives me 14.3%. Now we've done a little bit of rounding here, but if we add up all these percents, we're happy to find that we end up with 100% of the energy, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.